Sequential logic circuits. Sequential logic circuits use flip-flops as memory elements, and in which their output is dependent on the input state. Unlike circuits that change state depending upon the actual signals being applied to their inputs at that time, sequential logic circuits have some form of inherent memory built in. This means that sequential logic circuits are able to take into account their previous input state, as well as those actually present. A sort of before and after effect is involved with sequential circuits. In other words, the output state of a sequential logic circuit is a function of the following three states: the present input, the past input, and the past output. Sequential logic circuits remember these conditions and stay fixed in their current state until the next clock signal changes one of the states, giving sequential logic circuits memory. Sequential logic circuits are generally termed as two-state or bistable devices, which can have their output or outputs set in one of two basic states: a logic level 1 or a logic level 0, and will remain latched, hence the name latch, indefinitely in this current state or condition until some other input trigger pulse or signal is applied, which will cause the bistable to change its state once again. The word sequential means that things happen in a sequence, one after another, and in sequential logic circuits, the actual clock signal determines when things will happen next. Simple sequential logic circuits can be constructed from standard bistable circuits such as flip-flops, latches, and counters, and which themselves can be made by simply connecting together universal NAND gates and NOR gates in a particular combinational way to produce the required sequential circuit. As standard logic gates are the building blocks of combinational circuits, bistable latches and flip-flops are the basic building blocks of sequential logic circuits. Sequential logic circuits can be constructed to produce either simple edge-triggered flip-flops or more complex sequential circuits, such as storage registers, shift registers, memory devices, or counters. Either way, sequential logic circuits can be divided into the following three main categories. 1. Event-driven, asynchronous circuits that change state immediately when enabled. 2. Clock-driven, synchronous circuits that are synchronized to a specific clock signal. 3. Pulse-driven, which is a combination of the two that responds to triggering pulses. As well as the two logic states mentioned above, logic level 1 and logic level 0, a third element is introduced that separates sequential logic circuits from their combinational logic counterparts, namely time. Sequential logic circuits return back to their original steady state once reset, and sequential circuits with loops or feedback paths are said to be cyclic in nature. We now know that in sequential circuits, changes occur only on the application of a clock signal, making it synchronous; otherwise, the circuit is asynchronous and depends upon an external input. To retain their current state, sequential circuits rely on feedback, and this occurs when a fraction of the output is fed back to the input, and this is demonstrated as the two inverters, or NOT gates, are connected in series, with the output at Q fed back to the input. Unfortunately, this configuration never changes state, because the output will always be the same, either A1 or A0, it is permanently set. However, we can see how feedback works by examining the most basic sequential logic components, called the senior flip-flop.